Now, let's explore one of the most powerful applications of coordinate geometry, proving properties of shapes. This is where we bring all our tools together to rigorously confirm what a shape truly is. Have you ever wondered how engineers, architects, or even video game designers can be absolutely sure that a structure is perfectly shaped, or that its components are aligned with incredible precision? They do it using coordinate geometry. By placing a shape onto the Cartesian plane using coordinates, we can then use our mathematical formulas to verify every single one of its properties. This ensures unparalleled accuracy in their plans and designs. Think of all the formulas we've learned as your very own proof toolkit. The gradient formula is your go-to for checking if lines are parallel or perpendicular. The distance formula is perfect for verifying if sides have equal lengths, which is crucial for proving things like squares, rhombuses, or isosceles triangles. And the midpoint formula is fantastic for checking if diagonals bisect each other, which is a key property of parallelograms and other shapes. Let's try a classic example. Proving a parallelogram. Imagine we have a quadrilateral, which is just a fancy name for a four-sided shape, with its corners or vertices located at A12, B45, C85, and D52. How can we be absolutely certain that this shape is indeed a parallelogram? Here's how we'd approach it, primarily using gradients. Step 1. Check opposite sides. A key property of a parallelogram is that its opposite sides are parallel. To prove this, we need to calculate the gradients of the opposite pairs of sides. So we'd calculate the gradient of side AB and the gradient of its opposite side CD. Then, we'd calculate the gradient of side AD and the gradient of its opposite side BC. Step 2. Verify equality. After calculating these gradients, we compare them. If the gradient of AB is equal to the gradient of CD, then AB is parallel to CD. Similarly, if the gradient of AD is equal to the gradient of BC, then AD is parallel to BC. Conclusion: if both pairs of opposite sides are proven to be parallel, then, with 100% certainty, we have just proven that the quadrilateral is a parallelogram. This is a powerful demonstration of how coordinate geometry allows us to precisely define and prove geometric properties, moving beyond just visual estimation to absolute mathematical certainty. Let's apply our Proving Shapes toolkit to something truly spectacular and uniquely Singaporean: the National Day Parade formation. During the National Day Parade, we see the incredible precision of the marching contingents and the mobile columns moving in perfectly synchronized formations. It's a breathtaking sight, but the question is, are these formations truly perfect? Mathematically speaking, let's take a closer look at a section of a mobile column. Our mission, proving a parallelogram, will use the coordinates of 4 specific vehicles in this mobile column, which we've labeled R27, S109, A95, and F13. Our goal is to prove that the shape formed by these 4 vehicles RSAF is indeed a parallelogram. Remember the key property: a quadrilateral is a parallelogram if its opposite sides are parallel, which means they must have the same gradient. Here's our step-by-step proof using gradients. Step 1. Calculate the gradient of side RS. Using the formula y2 minus y1 over x2 minus x1, we get 9 minus 7 all over 10 minus 2. This simplifies to 2 over 8, which reduces to 1 over 4. Step 2. Calculate the gradient of side FA. This is the side opposite to RS. Using the formula, we get 5 minus 3 all over 9 minus 1. This simplifies to 2 over 8, which also reduces to 1 over 4. Since the gradient of RS is equal to the gradient of FA, we can definitively say that RS is parallel to FA. One pair of opposite sides confirmed. Step 3. Calculate the gradient of side RF. Now for the other pair of opposite sides. Using the formula for RF, we get 7 minus 3 all over 2 minus 1. This simplifies to 4 over 1, which is simply 4. Step 4. Calculate the gradient of side SA. This is the side opposite to RF. Using the formula for SA, we get 9 minus 5 all over 10 minus 9. This simplifies to 4 over 1, which is also simply 4. Since the gradient of RF is equal to the gradient of SA, we can definitively say that RF is parallel to SA. Our second pair of opposite sides is parallel. Conclusion: because we have successfully proven that both pairs of opposite sides are parallel, we can confidently conclude that the formation RSAF is indeed a parallelogram. Mission accomplished. This shows how math helps ensure the stunning precision you see at NDP.